Okay, so it's a minute past the hour. We'll get started. I'm Patrick Brady, and I'm the spokesperson for the LIGO Scientific Collaboration. Today, we're having another in our series of webinars reporting on recent results that have appeared in publications from the Observing Run 3. And I'm going to just hand over right away to your moderator for today. That's Eric Thrain, and he'll introduce both the webinar and the speakers. Eric.
Thank you, Patrick, and welcome to everyone. Thanks for joining us today. I'm Eric Thrain. I'm a professor of astrophysics at Monash University in Melbourne, in Australia. Let's go ahead and meet our panel that will be speaking today.
Hello everyone, I am Simone Mastrogiovanni and I am a postdoc at the University of Paris at the Astroparticle and Cosmology Laboratory.
Hi everyone, I'm Shanika. I'm a PhD student from Monash University.
Hi, I'm Tom Collister. I'm a postdoc at the Simons Foundation Center for Computational Astrophysics.
Hi, I'm Maya Fishbach, and I'm a NASA Einstein postdoctoral fellow at Northwestern University.
Today's talk is on the population properties of compact objects from the second LIGO Virgo Gravitational-Wave Transient catalog. We encourage you to ask questions during the talk using the Q&A feature, which, depending on your Zoom, is either at the bottom here or at the top here. Basically, you can type questions and our panelists will be able to answer some of them as the talk goes. We'll also take some questions via that Q&A feature at the end and give you verbal responses. And with that, I'm going to mute myself and we will begin our talk.
Thank you very much, Eric. So we go to the next slide, please. So this was the picture that we had during our first observing run with the two LIGO detectors. At that time, we know that there were several black holes that we observed via electromagnetic observations and also several neutron stars. During our first run, in 01, we observed the 3 binary black holes with gravitational waves. Less than a year later, we improved our detectors in the meantime, and we started a second run. Next slide, please. Which we called O2, and this is the first run in which also the detector Virgo joined the two LIGOs. And in this run, we detected 7 binary black holes and the first multi-messenger observation of a binary neutron star with gravitational waves. Now, after 1 year and a half of detector improvements, we made another run. Next slide, please. This is our O3 run. And in the first 6 months of this run that we call O3A, we have detected a large number of binary black hole coalescents and possibly also binary neutron stars. Next slide, please. So to summarize, as we improve our detectors, we are detecting more and more gravitational wave events. Indeed, during the first observing run, of 1 in just 4 months of data, we detected 3 confident binary black holes. During O2, in just 8 months of data and 3 detectors, we detected 7 confident binary black holes, 1 confident binary neutron star, and finally, in these first 3 months of O3A, we detected 1 event consistent with the masses of a binary neutron star, GW190425, 2 events consistent with the primary mass of a black hole plus a lighter object, GW190814 and GW190426, and 36 consistent events consistent with the binary black holes. On the right part of the slides, you see just a snapshot of our observation history with respect to the observing time, so the data taking, which is on the horizontal axis. As you can see, during O3, we had a significant increase of events detected. And this is due to the nice improvement on the sensitivity of our detectors that extended our range for detecting gravitational waves. During O3A, we had an average of 1.5 detections per week. Next slide, please. But what are we looking at with our gravitational waves? We are mostly detecting compact binary coalescences. These are the merger of 2 compact objects that can either be 2 black holes, 1 neutron star and a black hole, or 2 neutron stars. So these binaries are characterized by several physical parameters that can be proper of the binary, and in these parameters we call them intrinsic, and these are the spins of the objects, the masses, their tidal deformability, and the ellipticity of the orbit. And there are also some parameters which are measured with respect to a detector. These are the time of arrival of the gravitational wave at a detector, or the time of the merger, a reference phase, the sky position, the luminosity distance, and the orbital orientation. By changing these parameters, also change the gravitational wave that we are going to observe in our data. For instance, in the top plot on this slide, I show several waveforms, gravitational waveforms, computed varying the masses of the source. You can see that by using masses which are heavier, the gravitational wave becomes shorter and shorter, but also stronger with its gravitational wave luminosity. These plots are generated for a gravitational wave detector with a sensitivity band that starts around 20 Hz and correspond to a source located at 500 megaparsec. But also the spins are very important in the gravitational wave waveform. You can see that if the binary has no spins, so spin 0, the signal that you observe is the one in the bottom plot, orange, while if the two compact objects have spin, which are disaligned with respect to the orbital angular momentum, the system undergoes precession, and so we observe additional modulations in the waveform. So by studying the waveforms, we can work out and got a measurement of spins, masses, and also other useful informations. Next slide, please. So out of our catalogs, we are provided with a set of posteriors on the parameters that we wish to study. These posteriors are basically evaluation and measurements of these parameters. Now in GWTC2, there are some key quantities which are important for this paper that are going to be presented. One are the estimation of the masses of the object, which you can see on the left. Those are posteriors. The other one is the mass ratio between the two. Then we have some spin parameters and the luminosity distance of the source. Now, just by looking at these plots, which are posteriors from a subset of our GWTC2 catalog, you can already see that many events have similar parameters. For instance, you will observe that most of them are compatible with a mass ratio equal 1, which means that they are compatible with equal mass components. Thank you for the pointer. While some of them might be exceptional or special. For instance, GW190814, for which the mass ratio is definitely not compatible with 1. So studying the population is very important to understand their properties and also to classify exceptional events. Next slide, please. So how we do that? We select all the events in our GWTC1 catalog, so O1 and O2, plus GWTC2 catalog, O3A, that has a false alarm rate lower than 1 per year, which means that there is the possibility that noise fluctuations will produce such type of candidate which are lower than 1 per year. If we do that, we end up with a reduced catalog for this paper of 2 binary neutron stars event, one event which has the primary mass of the black hole and an unknown lighter object, GW190814, and 44 confident binary black hole events, which are the main focus on this paper. We use an hierarchical Bayesian analysis using several prior models on masses, spins, redshift distribution, and rates. In particular, we use 4 mass population models, 3 spin population models, 1 redshift evolution model. And we model in our analysis selection effects, which are important to understand if an event is detectable, because it is more likely to be detectable in our detectors. For instance, higher massive events are more detectable because they are louder, or if we don't detect them, because we are not sensitive to them. And with this, we go to the next slide, please. So in this paper, we're going to answer these questions. Are there binary black hole systems with component masses higher than 45 solar mass? What is the minimum mass of a black hole? Is there a preference to form nearly equal mass binaries? How fast and how misaligned binary black hole spins? And does the merger rate evolve with redshift? And with this, I leave the floor to Shanika for the next part of the presentation.
Thank you, Simone. So in this section, I'll be talking about the mass distribution of binary black holes. So by studying the 44 confident detections of binary black holes, we can uncover what the mass distribution looks like for this population. And this distribution can give us insights on some stellar evolution processes and how black holes form. So looking at this mass distribution here, we can learn a number of things, such as at the low mass end, we can learn things such as the minimum mass of a black hole, whether the shape of this distribution is sharp or smooth at this low mass end. And at the high mass end, we can look for features such as whether there's a cutoff, whether there's a tail in this distribution. And throughout the distribution, we can look for features such as peaks or dips. And for our analyses, we explore multiple different mass models to study our population of binary black holes. And these models have features that are motivated by astrophysical processes. So in the next few slides, I'll describe a few examples that motivate some of our mass models. So moving on to the next slide. So starting at the low mass end of the distribution, we can look at things such as what's the minimum mass of a black hole, but we can also look for the shape at the low mass end of the distribution. So looking at the plot on the bottom left, we can study whether we see a sharp cutoff or whether it's more of a smooth distribution. And features like this may give us hints as to whether there's a low mass gap. So looking at the cartoon on the right, this low mass gap is the possible gap between these really massive neutron stars, the most massive neutron stars and the smallest black holes. So by determining the minimum mass of a black hole and the shape of the distribution at this low mass end, we can start resolving this structure at the low mass end. So that's one end of the distribution. So what about the high mass end? So moving on to the next slide. So at the high mass end of the black hole distribution, we may expect a cutoff, and this cutoff is motivated by a process known as Pear instability supernova. So very massive stars, greater than 130 solar masses at zero age main sequence, or ZAMS, and this can be thought of as the original mass of the star. These stars would have enough energy to create positron-electron pairs. This pair production results in reduction of the outwards pressure of the star, causing the core to shrink. And this contracted core increases in temperature and is dense enough such that the heavier elements in the core fuse, releasing an immense amount of energy. And this energy is so immense that the star gets completely blown up. There's nothing left behind, so we don't have a remnant. So what this means is at a certain stage, stars collapse to become black holes. So stars can collapse to become black holes, but in this case, these stars completely blow up, so we don't have these black holes. So we expect this high mass cutoff. So what happens, so to refer to the plot in the bottom left, so we expect to see this cutoff at the high mass end of the distribution. So moving on to the next slide, we can look at what's happening for slightly less massive stars. So stars ranging from about 80 to 130 solar masses at zero age main sequence, these stars may undergo a process known as pulsational pair instability supernova. So this is similar to the process before. So looking at the cartoon on the right, these stars are massive enough again to produce these positron-electron pairs, and this also results in a decrease in the pressure outwards of the star, causing the core to contract, and this ignites heavy elements. But in this case, the energy pulsed outwards only results in the star shedding mass, and this process happens over and over again. So it sheds mass in pulses and down to masses below this mass range. So the key thing here is that these stars are shedding mass and then undergoing a core collapse supernova to form black holes, which means that there's a range of stars that via this process become similar masses and therefore collapse down into black holes of similar mass. So, and this mass range is around 35 to 45 solar masses for these black holes. So looking at the plot on the bottom left, we expect this kind of peak-like structure in the mass distribution before the cutoff, if we have this process. So these are some of the motivations or astrophysics that's behind the things that motivates the models that we used in our population analyses. So now let's have a look at what our results actually look like. So moving on to the next slide, thank you. So here are our population results from GWTC2. And so the plots here represent the reconstructed primary mass distributions for different models, and the primary mass being the more massive black hole in our binary. So the top left model is the truncated model. This model is a power law with sharp cutoffs at the upper and lower ends of the distribution. On the top right, we have power law peak. So this distribution is a power law, but it also has a Gaussian peak at around 40 solar masses. And it also, instead of a sharp cutoff at the low mass end, we have a smooth turn on instead. On the bottom left, we have broken power law. This model also has a smooth turn on at low masses, but instead of a peak, we have a break. So this model is actually two power laws, and when they meet, you have a break point if they have two different slopes. And finally, on the bottom right, we have this multi-peak model. So this model is kind of explained in the name. It has multiple peaks, and the additional peak at high masses is motivated by the possibility of a different population of black holes, possibly hierarchical mergers, which Tom Callister will talk about later on. So these are our results using the 44 confident binary black holes in our catalog. So let's look at some of the specific features that we see in these models. So we have these peak like structures, and we see these break-like structures. And of these models, we can determine which ones are more favored. So when we use multiple models for our analyses, we can do model comparison. And so we find that power law peak, multi-peak, and broken power law are our favored models, and truncated is disfavored, which suggests that a simple power law doesn't really explain our mass distribution. So moving on to the next slide. So let's look at our low mass distribution features a bit more closely. So the plot on the right shows some analyses with without GW190814. So GW190814 was an event that had a 23 solar mass black hole and a 2.6 solar mass lighter object. It may be a black hole, it may be a neutron star, just indicating here that this doesn't include that event because it's not a confident binary black hole. And so in this plot, this shows the 1D posteriors or 1D distributions and the 2D distribution for these parameters M-min, which is the minimum mass of the black hole distribution, and delta M, which is the smoothing parameter. And delta M equals 0 indicates that we have a sharp cutoff in our distribution. For larger delta M's, it means we have a more smooth-like distribution. So what we can see from this plot is that we exclude this region near delta M equals 0 and M min equals 2. So what this means is that you either have a sharp cutoff at around 4 to 6 solar masses, or you have a more smooth distribution that spans the range of solar masses down to 2 solar masses. And we find from our models that our models prefer a smoother distribution over a sharp cutoff. So what we're starting to resolve here is the structure at this low mass end. And in addition to our population study with the 4 confident binary black holes, we also do a study with our less confident black hole binary, possible black hole binary 1908-14. And what we notice is when we include this event, the low mass end of our distribution is pulled down from 6 solar masses to around 2 solar masses. And we determine that this event is an outlier when compared to the rest of the population. It only has a 0.02 chance of being drawn from our population of binary black holes. And you can find more information about this event on the link highlighted here on this slide. So those are our low mass distribution features. So moving on to the next slide. So one of the things we see in our mass distribution that there is structure beyond just a simple power law. So we have support for a peak-like structure and a break-like structure. So looking at the plot on the left, we have what this is showing is the fraction of binaries in our Gaussian peak component. We have so 10% of the population is in this peak. And zooming into the lower left-hand corner of this distribution, it excludes 0. So this suggests that there is this peak-like structure when we do our analysis with this model. And on the right, we have a plot comparing the 2 slopes of our broken power law model. And the dashed line represents when the slopes are equal, meaning that it's essentially 1 power law. But what you'll notice is that this is excluded. The distribution excludes this dashed line, which suggests that we do have a break feature, and our observations prefer a broken power law compared to a single power law. We also find that power law peak is our most preferred model, not by much compared to the broken power law, but compared to our truncated model, which is a simple power law with sharp cutoffs, it's preferred by a factor of 100 compared to the simple power law. So what we find is there is structure beyond just a simple power law in our mass distribution. So moving on to the next slide. What we also see is that there are masses beyond 45 solar masses in our mass distribution. So going back to the idea of Pear instability supernova, we expected this cutoff at high masses. We don't really see this abrupt cutoff, and that's also evidenced by the presence of 1905-21. So that is the most massive event that we've detected to date. And this event is in the tail of this distribution. And what we find when we do our population analyses, looking at this plot on the right, we compare the distribution that we get with and without 1905-21. And this event is consistent with our population. So it doesn't appear to be an outlier. So that's interesting. And also, if it may be in the tail of this distribution, but it might also be a separate subpopulation. We're unable to conclude this at this stage, but it may be part of this population, or it may be in a separate subpopulation, for example, hierarchical mergers. And the links below are the links to the papers on 1905-21. So that's the end for the mass section of this talk. So I'll hand over to Tom Callister to talk about spins.
Okay, thank you, Shanika. So yes, so now we're going to switch gears from mass and go to talking about what we now know about the spins about binary black holes. So just like Shanika explained how knowing about the mass distribution of binaries tells us a great deal about the relative astrophysics, the astrophysics behind stellar core collapse and black hole production. So too can we learn a lot of astrophysical information by looking at the distribution of binary black hole spins. So in particular, I think one of the most exciting questions for us in gravitational wave astronomy is how you actually go about forming binary black holes. We know they exist and we know they merge because we can see them in LIGO and Virgo. But if we try and rewind the clock and ask how those binaries were actually assembled, we don't yet know the answer to that question. This slide shows two possible answers. There are many others. I just want to be clear, but these are two of the most popular answers. So the top row traces out one scenario in which black holes are born from isolated stellar binaries through a mechanism called common envelope evolution. So in essence, these black holes are due to stars that were born, grew old, and then died together. So if we go from left to right here, we start out with some bound stellar binary. Now at some point, the star on the right will die. It will collapse and turn into a black hole. Meanwhile, as the second star on the left ages, it will swell up. And if it swells up enough, it will encompass the partner black hole. And this is called the common envelope stage. Now, what that common envelope will accomplish is it will draw the stellar binary closer together, the core of the left-hand star and the black hole on the right. In drawing the binary together, it will eject the envelope. And eventually, if now that left-hand star also collapses to form a black hole, what we're left with is two black holes on a very close orbit that will eventually merge via gravitational wave emission. And now what's key here is that it's thought that if binary black holes evolve in this way, their spins, if you look at their rotational angular momenta, their spins will be preferentially aligned with their orbit. Now, an altogether different possibility for binary black hole formation is dynamical assembly in dense stellar clusters. So here, these were black holes that did not know about each other early in life. Instead, they were born as stars and died separately. And then just by virtue of flying around in some very dense cluster, randomly encounter one another and capture onto some binary orbit. From this point on, that binary can be repeatedly pinged by other binaries as it's getting repeatedly pinged by other black holes zipping past. Its orbit might shrink, and it might even exchange binary partners. So for instance, in the third step here, some more massive black hole zooms by and swaps into the binary at the expense of the light black hole on the right. But again, at the end of the day, you end up with a close black hole binary that will also eventually merge under gravitational radiation. Here, though, because the black holes did not know about each other at birth, you generically expect the spin orientations to be random, both with respect to each other and with respect to their orbit. And so if we can go out and measure the distribution of spin orientations from binary black hole systems, this gives us a potential key to discerning between these and other channels and figuring out how binary black holes are born and how they evolve. So next slide, please. So before talking about some of our results, it's useful to just define some geometry. And in particular, we can talk about spins a few different ways. So the diagram on the right shows a cartoon of a binary black hole system. Here, L is the total orbital angular momentum. And the spins of the two black holes, their spin angular momenta, are denoted by these vectors chi1 and chi2, respectively. So in particular, chi1 and chi2 will refer to the magnitude, the size of those spin vectors. At the same time, if we want to characterize their misalignment relative to their orbit, we can talk about their polar misalignment angle, theta1 and theta2. Now, at the end of the day, chi and theta are the actual physical parameters that are describing the system. And so that's what we would really like to learn about. However, the actual spin magnitudes and tilts of individual black holes in these binaries are rather hard to measure. And so sometimes it's easier to quantify these so-called effective spin parameters. So these are defined on the left. And there are two effective spin parameters that we will look at. The first is called the effective in-spiral spin. And so this is the projection of each component spin onto the orbital angular momentum, or parallel to the orbital angular momentum, and then weighted or averaged together. So this is a mass averaged angular momentum, spin angular momentum parallel to the orbit. Chi effective ranges between 1 and -1. If you see a chi effective of 1, it means that both black holes are maximally spinning. They can literally spin no faster, and both spins are perfectly aligned with the orbit. If you have chi effective of -1, it means that, again, both black holes are maximally spinning, but both of those spins are entirely anti-aligned with the orbit. So if chi effective quantifies the degree of spin along this vertical axis, this other effective parameter we have, the effective precessing spin, quantifies the degree of in-plane spin angular momentum. So it has a much less intuitive formula, but it is effectively the degree of, again, in-plane spin. And it ranges between 0, if you have exactly 0 in-plane spin, and 1, maximal spin that sits in the plane of the orbit. Okay, next slide, please. So before talking about our updated O3A results, we can go back quickly and talk about what we knew before O3A, what we knew from the first 2 LIGO Virgo observing runs. So this plot shows for each of the 10 binary black holes in those first 2 observing runs are constraints on this effective spin parameter of each of those 10 binaries. Each of the violin plots shows a probability distribution on that parameter for each system. Now, each violin plot has 2 sides, which shows the results that we get under 2 slightly different assumptions. But the thing that you should take away from this is that all of these chi effectives are small. If you remember that chi effective can range between -1 and 1, here these are all clustered near 0. And so what this is probably telling us is that black holes have small spin magnitudes, but it does not tell us about their orientations. That remained largely unknown following O1 and O2. Next slide, please. Now, however, by virtue of O3, we have a vastly increased sample set. So these are the chi effectives of all of our new binary black holes. And with a much larger sample set, we can make much more sensitive statistical statements about the nature of black hole spins. And so that's exactly what we're going to do next. So next slide, please. Okay, so we took a few different, we adopted a few different strategies to investigate the distribution of binary black hole spins. First, again, what we really want to know is the actual distribution of the physical spin magnitudes, chi1 and chi2, and their tilt angles. And so one approach, which is called the default model in the populations paper, sought to measure directly the population distributions of these spin magnitude and spin tilt angles. However, because at times it's easier to work in terms of those effective spin parameters, we also took, in parallel, a more phenomenological approach and tried to ask, what is the distribution of these effective spins? What are the chi effective and chi p distributions? Finally, a third path that we took, called the multi-spin model in the paper, helped us understand whether there was evidence for what are called hierarchical mergers in the binary black hole population. So just to say a little bit more about this, if you merge 2 black holes, you will produce their remnant will be some larger offspring black hole. But you don't have to stop there. You can take the black hole that you have just formed, and it itself can merge again with yet another black hole, and so on and so on. And so particularly in dense clusters where there might be many black holes zipping around, you expect this hierarchy of mergers where merger products themselves undergo 2nd and maybe 3rd generation mergers. If that is happening, then generically you expect these hierarchical merger products, the results of 2nd and 3rd generation mergers, to be 1, both more massive, but 2 more rapidly rotating. And so one path to discerning whether those exist is to look for systematically higher spins at higher masses to see if there's a degree of correlation. So because we have finite time, I'm just going to talk actually about the middle, the second of these 3 approaches. But if you are curious about any of the others, please do ask in the Q&A or at questions at the end. Okay, so next slide, please. So in this Gaussian model, in this phenomenological approach, we said, okay, let's try and look at the chi-p values among the binary black holes that we see. Again, this is the degree of in-plane spin. And let's try and measure the mean and standard deviation of those chi-p values across the binary black hole population. In this plot, this is called the corner plot, shows our results. So the topmost subplot shows our resulting probability distribution for the mean of chi-p. The rightmost plot shows our probability distribution for the spread, the standard deviation. And then the middle shows the joint probability distribution inferred on these parameters. And now neither of these parameters are constrained terribly well. We still don't know quite what the chi-p distribution looks like. But the key is if you look at the bottom left-hand corner of this joint corner plot, where the mean and the standard deviation both equal 0, that possibility is confidently ruled out. So in other words, if every black hole had a chi-p of 0, the population would live in that bottom left-hand corner. So we are ruling out a delta function distribution of 0, or in other words, confirming that even if we don't know the shape of the chi-p distribution, there are broadly among the binary black hole population systems with tilted spins, that have non-zero in-plane spin components. And so that's rather exciting. Next slide, please. So we can ask essentially the same question, but now about the effective in-spiral spin. So now about the degree of spin parallel or anti-parallel to the orbital angular momentum. If you look at the blue curve on the right, this shows our results. So here I'm not showing a corner plot like I did in the last slide, but rather I'm showing directly our constraints on the shape of the possible chi-effective distribution. The light blue band shows our uncertainty region, and the solid blue line essentially shows our current best estimate, integrating over all of our uncertainties. And the key thing to take away from this plot is that if you look at negative chi-effective to the left, the distribution of chi-effectives is constrained to be non-zero there. We say confidently that a non-zero fraction of binary black holes have negative effective spins. In particular, taking into account our uncertainties, we infer that between 12 and 44% of systems live on this negative chi-effective side. So what makes this interesting is that in order to have negative chi-effective, that can only happen if at least one of the spins in your black hole system, in your black hole binary, is tilted by more than 90 degrees with respect to the orbit. And that, if you remember from a few slides ago when we talked about formation channels, that is very hard to do in the case of isolated binary formation. In particular, if you're willing to assume that negative chi-effective tilts by more than 90 degrees can be attributed to dynamical formation, then what you infer is that somewhere between 25 and 93% of the binary black holes we observe originate from dynamical channels. So this is clearly this estimate is still very uncertain. Many, many tens of percent uncertainty here. But this is exciting since this is essentially the first time that we can begin to probe this mixture fraction. As we continue to observe more events in O3b and beyond, this estimate will only get more precise. So now I think we're going to turn it over to Maya, who will tell us about our inferred rates of compact binary mergers. Thank you.
Yes, thanks so much, Tom. So the last part of this talk will be about what we infer for the merger rates. So in this paper, we infer the merger rate of both binary neutron stars and binary black holes. For binary neutron stars, we only have confident detections in this gravitational wave catalog and from the second observing run. And we infer that the merger rate is around 320 plus 490 minus 240 mergers per cubic gigaparsecs per year. That roughly corresponds to around 32 mergers in a Milky Way-like galaxy per million years. For binary black holes, we now have more than 40 of these, so we can simultaneously fit for the mass distribution that Shanika talked about, the spin distribution that Tom talked about, as well as the merger rate. And if we assume that the merger rate density is constant across cosmic time, we infer that average, it's around 23 mergers plus minus 9 per cubic gigaparsecs per year, which roughly corresponds to 2 binary black hole mergers in a Milky Way-like galaxy per million years. So moving on to the next slide. For binary black holes, we also looked at how the merger rate may have evolved across cosmic time. So for some context, this plot on the right shows the merger rate as a function of redshift that we inferred from GWTC1. So using just the first 10 binary black holes, we measured the merger rate as a function of redshift, where here higher redshift means we're looking back further in time. And in the first catalog, we measured that today, so a redshift equals 0, the merger rate was between 4 and 77 mergers per cubic gigaparsecs per year. And as we went back to higher redshift, so at redshift 1, 8 billion years ago, we inferred that the merger rate was probably higher, but we had more than 4 orders of magnitude uncertainty on that rate. So moving on to the next slide. So one of the really exciting results in GWTC2 is that we now have a much tighter constraint on the merger rate across cosmic time, because we have more events and we're able to see them out to further redshift, which is enabling us to probe the rate at higher redshifts. So this plot shows the rate of binary black hole mergers on the y-axis as a function of redshift on the x-axis. And we measured that today at redshift 0, the binary black hole merger rate is between 10 and 35 mergers per cubic gigaparsecs per year. And now as we go back and look at times in the past at redshift 1, 8 billion years ago, we now actually have a meaningful constraint on the merger rate, that it's between 60% and times its present rate. Moving on to the next slide. So what we're actually doing when we're fitting for the evolution of the merger rate is fit a model rate as a function of redshift varies as 1 plus z, the redshift, to kappa, and we're fitting for this index of the merger rate evolution kappa. And here's the posterior probability that we infer for this index of the redshift evolution. And there are 2 values here that we've marked out. Kappa equals z corresponds to no evolution. So the rate is constant across cosmic time. And kappa of around 2.7 is close to the evolution that tracks the star formation rate in low redshift. So you can see the bulk of our posterior inference is between these 2 values. So the most likely values for the evolution of the merger rate is between something that doesn't evolve at all, 0, and something that evolves as fast as the star formation rate. So this is well in line with expectations for binary black hole formation, in which the progenitors of the black holes track something close to the star formation rate, but then there's a delay. So the peak of the merger rate happens at lower redshifts. So moving on to the next slide. We've now covered the three main topics of population inference. That's all in this paper. And so now I'll just spend some time concluding the main results. And as we go along, feel free to drop questions in the chat. So the astrophysical lessons that we have from GWTC2, what we've learned about the mass distribution is, first, the black hole mass spectrum does not terminate abruptly at 45 solar masses, which we had hints of from GWTC1. However, it does still show a feature at 40 solar masses, so that feature that we thought might have been a cutoff from the first catalog is still there in the data, but we now know it's not a sharp cutoff. So it's probably better represented by either a break in the power law at around 40 solar masses or a peak at around 40 solar masses, after which there's a higher rate of decrease in the merger rate as a function of mass. Second point that Shanika touched on is that there's a dearth of low mass black holes between 2.6 solar masses, which is where we have that mystery object, the secondary of GW14, and 6 solar masses. So we don't see any black holes in between that range, and maybe that's starting to be statistically significant. A third lesson that we have about the mass distribution is that the distribution of mass ratios is broad. So unlike in GWTC1, where we thought that perhaps all binary black holes were made out of equal mass component black holes, we now know that the mass ratio distribution extends to more extreme mass ratios, spanning the range around 0.3 and 1, although there's still a mild preference for equal mass pairings. And here, GW190814, that extreme mass ratio event with the 2.6 solar mass secondary, it's still an outlier in the mass ratio distribution. So moving on to the next slide. Here are some of the lessons that we have about the spin distribution. So as Tom said, we know that some binary black holes have measurable in-plane spin components. So we rule out perfect alignments of the component spins. This leads to precession of the plane. Second, we know that some binary black holes have spins that are misaligned by more than 90 degrees. On the other hand, the distribution of spin tilts is not perfectly isotropic. So it seems like more binary black holes have aligned tilts than misaligned tilts, which suggests that there may be multiple formation channels producing the black holes that we see. And there are hints, but not yet any clear evidence that the spin distribution varies with mass. So moving on to the next slide. So some conclusions about what we infer about the rates of these mergers. So we know that in the local universe, the average binary black hole merger rate is between 15 and 40 mergers per cubic gigaparsecs per year. And the binary black hole merger rate probably evolves with, but slower than the star formation rate. So the merger rate probably increases by a factor of 2.5 or so between redshifts of 0 and redshifts of 1. So next slide. So as I hope is clear by now, there's really a lot of information and a lot of discoveries that we've made with this latest batch of binary black hole detections from LIGO and Virgo, but we've also raised a lot of open questions. So I've listed some of these questions here. What is the physical origin for the feature at around 40 solar masses? We know it's not a sharp cutoff, but there's still something there. Is that pair instability what is causing that. And then what's the origin of black holes with masses above 45 solar masses? So if the feature at around 40 solar masses is the imprint of Pear instability, is there a subpopulation that's contaminating the gap? Is Pear instability just not a sharp cutoff? What's going on with those high masses? And then third, is there a mass gap between neutron stars and black holes? If there is a mass gap, what is the nature of that 2.6 solar mass object in GW 190814? That event still, it's an outlier in our models, and we still don't have a good explanation for it from the data. Another question is, are the systems with misaligned spins the result of dynamical assembly? And because we know that it's fewer than 50% of systems have misaligned spins, so the distribution is not perfectly isotropic, are we observing binary black holes from multiple formation channels? And if so, what are all of those formation channels? So these are still very open questions that we hope to answer with future data. And with that, I think the next slide is just a thank you. So thank you to everyone in the LIGO and Virgo collaboration for producing these results. And thanks to all of you here for listening. And I think we'll now turn it back to Eric.
All right, thank you to our panel members for that very nice presentation. I will see if I can pull up the Q&A, and I think we have time for some questions. So the one at the top of my feed is from Alejandro Vino Gomez. Hi, Alejandro. And this has 3 upvotes. Alejandro asks, are the waveforms currently used good enough or adequate to make accurate inference about spins, particularly thinking about large misalignments and negative chi-effectives? And I'm going to toss this one to Tom.
Yeah, thank you for the question. So my disclaimer from the outset will be that I am not, there are people within LIGO who are, have more expertise in waveforms than I do. But I think that's a really good question and a really good thing to be aware of. And so I think there are a couple different answers to this. This is sort of subtle. I think that where you don't, the regime where you don't trust waveforms is the regime where you have very large spins. So chi1 and chi2 values that are close to 1. I think that is where there's sort of perhaps demonstrated incompleteness. Fortunately, sort of counterintuitively, the fact that we're finding that spins are small, even if they're misaligned, their magnitudes seem to be preferentially small, sort of safeguards us from that. Another thing that we tried to do to safeguard us from waveform issues is that all of these results use parameter estimation results from multiple different independent waveform families. And so the hope is that we've taken into account essentially model uncertainty in constructing waveforms. There are things that we learned we did have to worry about. So in particular, a different waveform effect, but one that ended up mattering, was including what are called higher order multipole moments in the radiation. Historically, waveforms have used just the lowest order radiation pattern, the quadrupole radiation. And it turns out that if you want to make accurate inference about the spin distributions, it does make a non-negligible difference if you include higher order radiation modes. So I think the quick answer to your question is I think we're safe, but we've definitely learned that we still need to be careful and on our toes looking out for waveform issues.
Thanks for that, Tom. I'm going to take the next question from Jessica Liu, who asked, do you have predictions for the number of binary black holes not yet merged in the Milky Way, so the galactic population? We might be able to find them with microlensing. And I'm going to toss this one to Maya.
Hi, yeah, that's a really good question. So we're really only sensitive to the population of black holes that do end up merging. So the population of black holes that never merge could be really different from that. So in terms of black hole mergers, we know that the rate for a Milky Way is quite small, only a couple per million years, but tying in this inference to other black hole populations, like tying in the gravitational wave observations of binary black holes to like black holes in our galaxy that are observed in X-ray binaries, that's still a very active area of research. So I guess it's a great question, and I don't have a great answer for it yet.
Thanks, Maya. I'm going to take the next question, and apologies if I butcher your name. Panagiotis, can the 2.6 solar mass object in GW190814 be a heavy neutron star? Is such a scenario supported by the rest of the data? And I'm going to pass this one to you, Shanika.
Hi. So with our analyses, we look for, I guess, we model the black hole population, and from our understanding that this is an outlier with respect to our current population, possibly. I'm not too familiar with what the conclusions in the specific 1908-14 paper was, other than it's possible that it's a large neutron star and it's possible that it's a very, very small black hole. So we're really just on this level of, we're uncertain on this topic, but it definitely is something that it would be interesting to look further into.
Yeah, I can add that in principle, you can get the tidal information in the gravitational wave signal, which can give you, that's a smoking gun for a neutron star, but it would have been too weak with 1908-14 if indeed the secondary was a neutron star. Okay, the next one is from Eric Burns. And okay. He writes, the lower inferred BNS merger rates seem to be driven in part by fewer detections with the longer, more sensitive run, but also due to the choice of the 2.5 solar mass upper mass limit in the uniform time prior. Could you comment on why this was chosen? Is it self-consistent with the data? I suspect that the gravitational wave and gravitational wave gamma ray burst rates from these events will be relatively unchanged, but gravitational wave kilonova would seem to be lower than previously expected. So this is a lot going on here, and I asked our panelist who wanted to take this one, and Tom put his hand up. So Tom, please go ahead.
So I can just maybe broadly speak to modeling choices, and I think you're absolutely right that there are two sources of uncertainty in these rate estimates. There is the counting uncertainty. There is some fundamental rate, and we observe for a finite time. And so there will be some variance on the number that we record. But then there's also systematic uncertainty associated with the model that we presume for the mass distribution. At the moment, my guess is that this former, this counting uncertainty is the vastly dominant source of uncertainty on the rate. And so we don't, this 2.5 cutoff, you could imagine very easily making other choices or settling on a different choice. But I think for now, those choices are subdominant to the counting uncertainty. Soon, though, this sort of mirrors the path that we had to take with binary black holes, where as you start accumulating a population, you can no longer make these arbitrary choices, but you have to self-consistently worry about fitting the distribution, the shape of the mass distribution, and the local merger rate. And so I don't think we're there yet, but as we accumulate more BNS candidates, I think we will soon get there. I can't comment on, I think, expected kilonova behavior, but I think that remains a really interesting question, what sort of EM signals you might expect from these more massive neutron star binaries.
Thank you, Tom. I am going to take at least one more question, and Patrick Brady, please let me know in chat if we should end there or take a couple more. But the at least one more question will be from Denitsa, who asks, is there an understanding about the connection between the observed merger rate and the star formation rate? And this is a one that I'm going to give to Simone.
Okay, yeah, so studying the mechanism that connect these two quantities is indeed very important, as Denise is saying. So basically, we would expect that the black hole formation rate will follow some kind of the stellar formation rate. So I mean, when in the cosmological history, it's more likely that stars are formed. Also, black holes can be more formed, or they can have a slight delay. And this is actually what we observe in the rate evolution. We know that our peak on the merger rate actually peaks a little bit below the expected star formation rate. I can't really comment on which is the actual mechanism and timescales that connect the two, but yeah, I think that's all.
Thanks, Simone. I'm going to go to C. Renee James next for the question. And Renee asks, is there enough data to suggest an evolution of the masses of black hole mergers with distance? Not just the rate, but the black holes involved. Is there evidence that they are gradually grabbing innocent passerby black holes? And I'm going to give this one to Maya.
That's a great question. There are, I guess, several aspects there. One aspect is are the actual population properties changing as we go higher, and we don't expect that to be the case at the relative low redshifts that we're still probing, basically because although the universe is changing a lot between 8 billion years ago and today, it did change a lot. But we expect that the time delays between the formation and merger to have a pretty broad distribution. So the black hole mergers that we detect at a given redshift aren't all formed at the same redshift. We're kind of mixing in the formation across multiple time periods in the universe. But it's definitely an area of active study, and with future generation ground-based gravitational wave detectors, we'll be able to see every black hole merger across the universe. There we really expect to see some change in the population based on the redshift at which they merge. Yeah, and then the other question, the other part of that is, are they like continuously grabbing other holes? So that relates to, is it possible for a black hole merged to merge again with another black hole? And that is this hierarchical merge scenario that we brought up a couple of, but didn't go into a lot of detail in analysis in the paper, the multi-spin analysis, which looks for this characteristic mass-dependent spin distribution that we would expect if our black holes formed from mergers of smaller black holes. We would expect them to spin faster than black holes that are born from stars. And we don't clear evidence for that yet in this paper, but it's definitely possible that some of the events we're already seeing are product of hierarchical merger, or the black holes that we've seen merge will a long time from now merge again.
Thanks, Maya. The next question I'm going to take as a topic dear to my heart is Jen Pan asks, why is the eccentricity information not included in your analysis? And I'm going to pass this one to Simone.
Okay, thank you for the question. So I would answer that the fact is that when the two compact objects they approach each other and they are very close, we expect the orbit to be almost circularized, and this is due to the gravitational wave emission. But it is indeed very correct to say that, of course, we would expect also other type of mergers, which can be which can be eccentric. We can expect also other type of merger like heads-on collision. And these are important to model inside the waveforms. And indeed, we have some efforts inside our collaboration to do that. I'm not aware from experts. There are people which knows a lot more, but it's a difficult task, especially when the orbit is precessing and the events are really spinning. So yeah, I think that's all.
Thanks, Simone. I'll go on to the next question. Does the delay in the peak rate of binary black hole mergers with respect to peak stellar formation rate hint at anything with regards to the average merger time for binary black holes with stellar progenitors? Does that help us constrain merger models further? And this is from Rahul Srinivasan, and I'm going to send this one to Maya.
Yeah, another really good question. So one disclaimer, I guess, is that we're not actually measuring the peak of the merger rate yet. We're only measuring the slope between redshift 0 today and where we think that the peak is, presumably at redshifts higher than 1 or so, which is as far as we're able to probe right now. But yeah, the fact that the merger rate that we're measuring is evolving with redshift at a rate that is probably slightly slower than we expect the star formation rate. So basically, we're observing that as we look out in redshift, the merger rate is increasing, but not as fast as we think that the star formation rate increases. So right now that we still have pretty broad uncertainties on that. They're a lot better than they were after the second observing run, but they're still pretty broad. So we're not able to yet like tease out in detail what is the time delay distribution. We're still pretty consistent with a range of time delay distributions, which basically just say that wherever the peak of the binary black hole merger rate is should be at lower redshifts than the star formation rate, and therefore the rate should increase a little bit slower. So we're able to match that right now, but not necessarily resolve between different models yet.
Thanks, Maya. I am going to now take a couple of questions together and pass them to Tom. They both relate to spin. So the first question comes from Louise, and Louise asks, why is there so much difference in the probability density from chi effective for GW170729? In particular, I'm asking about the different methods shown in the violin plot. And I think this is the two posteriors on the, okay, Tom's nodding, great. The second question, I'm gonna, before you answer that one, so you can be mulling over both, is it possible to infer deviations from general relativity by looking at spins? And that one comes from Tatiana de Paulo Moraes. Sorry for these names. Take it away, Tom.
Yeah, so I'll try and answer those in orders. So first, Luis's question. So first, good eye, catching that. So if you remember in the spin section, when introducing spins, we looked at a plot, this so-called violin plot. And each event had two different violins that had different colors. And I just sort of vaguely said that those were results under different assumptions. So in particular, just to be a little bit more formal, what is different for both sides of these for a given event is what's called our prior assumptions, what we probabilistically believe in advance about the spins of each of these objects. Now, for each event on the left side, to get that answer, the answer on the left, we assumed very little a priori about the spins that we expect. And in particular, we looked at each event in isolation, sort of in its own truly isolated universe, and asked, what does the data tell us about the spin of that event? To get the answers on the right-hand side in white, we took a different approach, which is, let's again ask this question, but now instead of looking at each event in utter isolation, let's look at it in the context, sort of holistically, the context of the population that we see among all the other binary black holes. Now, 170729, well, okay, so first, all of these look largely similar on the left and right hand sides, except for 170729, which shifts not by a ton, but considerably. And so the reason for this shift is the fact that 170729 is sort of special here in that the spin is inferred to be large when you look at this event in isolation. And I should be careful, not large as in close to 1, but large relative to the others. Now, there are two ways to explain a measurement of large spin here. One is that 170729 could just truly be rapidly spinning. It could actually have a chi effect of around 0.4. But the other way to get that measurement is to remember that we have our measurements with LIGO are noisy. There is some uncertainty associated with them. And in particular, there are random errors. And we know the typical size of those errors, but we don't know which way those errors will swing for any particular event. So if you look at the other 9 black holes here, and you say that all of those had small spins, and then you look at 170729, you can ask, what is more probable? That this event truly had large spin, or that this event had small spin like all the others, and it was just a particularly unlucky swing in the error in the measurement that gave it a large spin. And so that effect, that sort of question, is taken into account in a rigorous way on the right-hand side. And so when you account for all the others, you favor a little bit more the second option, that its spin is actually a little bit smaller. You just got an unusually large fluctuation in your errors there. So I hope that answers your question. Okay, the second question, which is from Tatiani, is about looking for deviations in general relativity using spins. Other people may have different thoughts about this. So if there are other ideas, totally chime in. My thought is that it's probably hard to test general relativity looking at the spins of the individual binary black holes as they are in spiraling. However, where spins might be really useful in testing general relativity is when you look at what happens right after the black hole system merges. So when you collide these black holes, they form some larger black hole. But in the instant during and after merger, that is not a particularly happy black hole. It is perturbed. It is like very distorted. And over time, it will ring, kind of like a gong or a bell. And as it rings, it will radiate gravitational waves and settle down to a nice, happy, unperturbed black hole. Now, the frequency of that ringing, the frequency of the gong, if general relativity is right, is predicted, is a computable function of the mass and the spin of that merger remnant. And so one way to test general relativity is to try and, compute the mass and spin of the remnant, predict the frequency of this ringing, it's called a ring down, and then compare it to what you actually see. If that matches, then this is consistent with general relativity. If it's wrong, then and I'm
going to jump in here, Tom. This is a nice opportunity.
Yeah.
Thank you for that answer. Just to give a shout out to the Tests of General Relativity paper, which I'd like to point you to. Link is here, or just Google GWTC2 tests of general relativity. And such tests as Tom described are in there. I've been notified that we are running out of time. So I'm just going to take one last question. And this one was from Lee. Sorry if this was already addressed, but is there a noticeable difference in the estimated or inferred merge rate and the amplitude of the gravitational wave background depending on the model used to measure the distribution of binary black hole spins? If so, what are the parameters that you value for higher selecting specific model? For example, using the Gaussian model over the default and multi-spin models. And my own paraphrase of this question is a two-part. I think the questions being asked here are, is the rate about the same depending on the different models that we calculate, that we apply, and also how do you know, what do you use to determine which models are preferred? I think that's my interpretation. And Shanika, is this one that you said you would take?
So not the question by Lee, but the question by Gavin, which I'm just typing right now in the chat.
Okay, so you'll do that one by text then. And Maya, or no, sorry, Simone, we haven't come to you in a minute. Let's end with you. Sorry to put you on the spot. Would you mind taking this question from Lee?
Yeah, sure. So, well, in our paper, we use just one spin model to infer the merger rates. So I think the answer here is that we should study that. Maybe Maya can say a little bit more about that.
Yeah, in terms of the merger rate, we expect that to be most degenerate with our inference on the mass distribution, actually, because the different masses, we can see them, the bigger masses, we can see them to higher distances. So there's that degeneracy with like the volume we're probing and the mass distribution. But we actually find pretty similar merger rates for all the different mass models that we use. And yeah, and in terms of like implications for the gravitational wave background, we'll also save that for a later paper by the LIGO and Virgo collaboration on the stochastic background. But yeah, that's it shouldn't vary very much between the different models for the mass distribution. That's at least at this point, it's a small systematic.
Thanks, Maya. I think with that, we are going to end with the Q&A session. Thank you so much to our panelists for the presentations and for sticking around for Q&A. Thank you to you, our audience, for joining us today to hear about this exciting science. Patrick Brady, did you want to say a quick goodbye before we close the session?
I will just do a quick shout out for the attendees that are still here for a webinar next week about tests of GR based on GWTC2. There'll be an announcement going out and it'll be back at our normally scheduled time, but watch for that advert.
Thanks so much, and see you all at the next LIGO Virgo webinar. Bye.